Today we're going to be talking about the wind triangle, which is essential for when we start talking about the forces and moments that act upon our aircraft. So let's go ahead and get started. The wind triangle, as we see here, this triangle is formed by three different vectors. We have V sub g, and I'll try to write that in bold. V sub g is our ground speed vector. Or ground speed velocity. So that's actually the motion of our aircraft. And so that's going to be how we measure, or not how we measure, but how we quantify the velocity of our vehicle. Then we have V sub w. This is the wind vector. And this wind vector is defined by weather, right? So we get a contribution from weather, basically the wind gusts that are currently happening at that instant in time. And then we have bolded V sub a. This is going to be our relative wind vector. In other words, this is the wind that the aircraft actually experiences. So there's going to be a component of the wind that is caused by the motion. So say that it was a perfectly clear day, no gusts at all. As the aircraft is moving forward, it's going to feel basically what it feels like is wind caused by its motion forward. And the V sub w also then will affect it. So now we have wind gusts, and we'll model those in a future chapter. But we have wind gusts that are occurring, and that's going to cause the aircraft to feel the effect of the air slightly differently, right? So we have these three different components, and so V sub a will be really quintessential for defining how the forces and the aerodynamic forces and moments affect the vehicle. So we can define this wind triangle using this relationship. This relationship is really important. We define V sub a is just equal to the ground speed velocity minus V sub w. Now we've already seen the elements of the ground speed velocity. These are u, v, and w. If you recall, those are the x, y, and z components of the velocity of the vehicle. Now we can define our wind is typically defined in the inertial frame, and you'll notice that we have a rotation matrix that'll take us from frame V to our frame B. Now, don't get confused over that because our inertial frame and the vehicle frame are parallel, right? And since this is a vector, it's going to be expressed exactly the same in both our inertial frame and our vehicle frame. There's just a translation between the two. So we have our northeast and down components, and we use this rotation matrix from the vehicle frame to the body frame, and that depends on our roll, pitch, and yaw angles, so phi, theta, and psi. And that'll give us our wind vector, so V sub w, in the body frame. So this is our wind vector in the body frame. So we can then relate this. We have our velocities of the aircraft, u, v, and w. That's our velocity in the body frame. And we have our wind vector defined in the body frame. So then we could very quickly then just take the difference between these two and get our relative wind vector in the body frame. And that's what we see down here. So we just have that our relative wind vector in the body frame. So this is relative wind vector in the body frame. And that's just defined as V sub g. Oh, sorry. I had V sub g in the body frame minus v sub w in the body frame. And these should both be bolded. And we call the difference UR, VR, and WR. So this is our relative wind speed in the body frame. Okay, so then we can take this, so this is our relative wind speed in the body frame. We're going to actually define a new frame. So this is our what we'll call the wind frame. And this can be slightly confusing because it's not going to be defined in terms of the vector v sub w. It's going to be defined in terms of the vector v sub a. But we'll still just call it the wind frame. And the wind frame, we'll define it, the wind frame. This guy will be defined such that their x-axis points along the v, I'll put bold there, sub a. You'll notice we have a bold over here, and we have just a scalar right here. This unscaled, or the scalar version of v sub a, this is just going to be our wind, what we call our wind speed, or we should call it our relative wind speed, but sometimes we'll kind of use those interchangeably. So we have our relative wind speed as v sub a, scalar version, and then we have the wind vector. And so you'll see here that when we're in the wind frame, all of our magnitude is centered on the x-axis. Okay, so we'll use that frame, and it'll be important for us. Okay, so these relationships are really important. Just to review, we have our ground speed velocity vector, v sub g, and in the body frame, we have our components of the vehicle velocity, u, v, and w. We also have our wind, and this is due to weather, right? The wind vector due to weather, we can define that in the body frame. All it is we're taking it from the inertial frame and we're rotating it into the body frame. And then we have our relative wind vector. Okay, now I did a funny thing and I accidentally mixed up the order of my slides, so we're going to jump up 2 slides here. So we're going to get to the wind frame. So again, the wind frame points along v sub a. We're going to get to the wind frame using 2 angles. And we're going to define the wind frame from our body frame. And this will be helpful later on as we're talking about forces and moments that act on our aircraft. So we're going to define 2 additional frames. The first is the stability frame. So now the stability frame, it's slightly different than what we've done previously, almost, right? So when we had talked about, we went from vehicle, we talked about going to vehicle 1, then we talked about going to vehicle 2, and then we went to the body frame. We just kept going forward in one direction. Well, we're going to take our stability frame, and we'll call S for short, and we're going to define it, the rotation that takes us from the stability to the body. So it would have felt a little bit more natural to just keep going in that direction, right, where we define our angle from the body to the stability, but we're not. We're defining, the book defines the stability frame, and the angle to get from the stability to frame to the body frame is this angle alpha. So alpha is called our angle of attack. Okay. So what it is we're just taking, we're going to do, if we look here, we define how alpha affects the rotation matrix, right? And we'll see we have cosine alpha, negative sine alpha, and cosine alpha. If we look at this, this is just a rotation r sub y. So that's we're just grabbing the body frame y vector, and we're going to rotate it by well, if we rotate it by negative alpha, then we get to the stability frame. If we rotate it by positive alpha, we're going from the stability to the body frame. So if we take a look at our little sim, I've got the wind already defined. So it's important to note that we've got the wind defined, and it can be in any arbitrary orientation with respect to the aircraft. And again, that's the relative wind vector that we're defining. So the relative wind vector would be along this red axis right here. So if we look at the stability frame, so we're going to turn off the wind. Well, we'll keep that on, and we'll turn on that. And I want to turn on the body frame in just a second. But our stability frame isn't quite to, and we'll turn that on and off so you can see which one it is. Our stability frame isn't quite to the wind vector, but what it is aligned with, you'll see that this plane of the wind vector that's formed by the green and the red axes, this plane is going to be the exact same plane. So if we now look at the stability frame with respect to the body frame, we could have kept our northeast down. Okay, what we've done here is we've rotated about the y-axis. So again, they share the same green axis, and all we're doing is we're taking it. Let's see if I can get a different view. So the body frame, you see that it's coming straight out of the aircraft, and what we're doing is it's basically as if we're pitching up a little bit more to get to the plane where the wind is acting. So we just have that pitch up. So we go from our body up into the stability frame. Okay. So now we have just this relationship. So if we want to go from our stability frame, so if we want to go from our stability frame to our body frame, we use this rotation matrix that we've already defined. And then the stability frame, it just helps us define that angle, this angle of attack. So we have that angle of attack, and it's going to be useful for analyzing the stability of the aircraft. Now, the important thing to note here, and this is just calling back on our properties of the rotation matrix. If we have something that's in the body frame, so if we want to go from something that's in the body frame and transform it into something that's in the stability frame, well, this is how we would write it. We would write it, the rotation matrix, from B to S, right? But all we have to do we define this matrix from S to B. So to get S to B, all we do is we take this transpose, right? Or I didn't say that very well. To get from RBS to RS from RSB, we just say that RBS is equal to RSB transpose. There you have it. So we're just using that relationship. So we can then transform something if we have an element defined in the body frame, we can then transform it into the stability frame pretty easily. Excellent. So that's our first transform, and the key here is this term. It's called our angle of attack. So again, that's our angle, basically our pitch angle with respect to the wind vector. So there you have it. Then we're going to jump into the wind frame. So the wind frame right here, and again, the wind frame is going to the relative wind vector. We just call it the wind frame for short. So we're going to have this angle beta. Beta is what's called. Beta is our side slip angle. Let me make sure I didn't miss anything that I wanted to point out. Okay, now we have our side slip angle, And what we're doing here, we can just identify it really quickly. Since we have this 1 in that bottom right corner, this is a rotation matrix. We're just rotating about our z-axis. So the stability frame and the wind frame share the same z-axis, and we're just rotating it about this side slip. So if we think about what the side slip is that and it's really easy to look at in terms of this flat, a top-down angle. It's just the difference between how we're moving, VG, and how we're how we're feeling that wind vector, right? So that's why we call it the side slips, because it feels like the aircraft is actually kind of slipping along. Now, if we go back to our visualization, let's take off the body frame. So we have the stability frame right here. And just to visualize it, now we have the wind frame. Again, we share the same z-axis. And now the I-axis right here will point along V sub A. So that angle of attack was to get us from the body frame, the nose coming out there, up into this vector I. And our side slip is now saying, hey, here, this is the angle between where the aircraft is pointed and how it's feeling the wind coming at it. Okay. Excellent. So we now have our side slip angle. It's a rotation about that z-axis. If we have a vector in the stability frame and we want to get it into the wind frame, we then just use this rotation matrix R sub S to W. Again, that's going to transform us from frame S to frame W, to our wind frame. Okay, then if we want to get our transform from our body frame to the wind frame, and which we will use quite a bit, either that or it's transposed to get from the wind to the body frame, we just chain these together, right? So again, all we're doing is we're just chaining these transforms. We have R sub S superscript W comes first, then R sub B super S comes second, multiply those together, and we end up getting this relationship. Okay, so we can define that transform in terms of our beta and alpha angles. Again, where alpha is our angle of attack, it's related to our pitch. Beta is that side slip angle, could be related a little bit to our yaw. Okay, so now the wind frame helps us define that side slip angle. Like I mentioned earlier, the forces and moments are most naturally defined in the wind frame. So what we'll do in a future lectures, we'll define how the forces and moments are acting on the aircraft, and then we'll transform it into how it's acting in the body frame. Okay. And then this R sub W to B, right? So this is just our rotation matrix to get us from the W frame to our body frame. All we do is we take the transpose of the matrix we had on the previous slide, and there you have it. So we can go from either the body frame to the wind frame or vice versa. And it'll be really helpful as we define our, as we end up defining various forces and moments. Okay, now we'll transition. We're going to talk about how do we get these angles based on our velocity vectors. So given recall this is our relative, the V sub A super B is our relative wind vector in the body frame, which we can obtain really easily. So we could obtain the airspeed. If we look at what the airspeed is, then if we know our alpha and beta, we can quickly get V sub A super B. But in reality, typically we don't have that directly. So, sorry, I misspoke. We typically we measure this. So this is what we can typically measure. So we can measure what our relative wind vector is in the body frame, and then but we want to get out what our alpha and beta, because that'll tell us how we're going to be affected. The forces and moments are going to affect our body or the aircraft. So we can define. We know this rotation matrix, so we know what, and we say we have our V sub A, and typically V sub A is we can obtain really easily. So if we've measured our relative air vector in the body frame, we have U sub R, V sub R, and W sub R. So let's write this out. So we measure UR, VR, and WR. Then we could really rapidly get V sub A. And what we're then going to also obtain is from that we'll get alpha and beta. So if we look at V sub A, right, that's just the magnitude of that vector. So very, very simple, just the magnitude of the vector we've measured. So we get V sub A. Then we can define alpha using some nice relationships. So if we look at this equation, you might wonder, where in the world did this come from? Well, if you look at WR, so defined right here, this is just going to be equal to VA sine alpha cosine beta all over. Now U sub R, so this is WR, U sub R is going to be equal to VA cosine of alpha cosine of beta. So taking a quick look at that, we can cancel out those terms, and what we're left with is the tangent of alpha. So we have tangent of alpha, which is something we can, so we just divide W sub R and U sub R, we're going to get the tangent of alpha. So we take the inverse tangent to get alpha. So we can rapidly solve for alpha, which is really nice. And we can do a similar thing for beta, right? So we can take beta and write it as V sub R over the magnitude of U sub R squared plus V sub R squared plus W sub R squared. And again, you can just use trig identities to do a very similar trick. One thing that's going to be helpful for us, we won't use this relationship quite as much as we will use that beta is equal to, and would write this as the inverse tangent of V sub R over the square root of U sub R squared plus V sub R squared. Okay, so how do we get that? And really, it's just using trig identities in a very similar fashion. But let's look at this piecewise. So at the bottom of it, we have the square root of U sub R squared plus V sub R squared. Okay, and again, remember we have U sub R and we have V sub R. Okay, so let's take a look at these. We'll end up getting this is equal to, whoops. Yeah, I'll zoom in so we can just write it out real nicely. It's going to be equal to, we're going to ignore VA because it's going to end up getting canceled out when we divide things out. So let's just look at the angles themselves. And so what we can write then is we have U sub R squared would be cosine squared alpha sine squared alpha, cosine squared beta. Maybe I should just bring back that equation so I don't have to look over so far. Okay, and then we end up having plus the V sub R squared is just going to be sine squared alpha cosine squared beta. right? And so we notice that we have a cosine squared beta on each of them. So this is equal to square root of, we have cosine squared beta, we have cosine squared alpha plus sine squared alpha, right? This guy, we can say that this cosine squared of an angle plus sine squared of an angle is just equal to 1. So we end up having the square root of cosine squared beta, which is equal to cosine of beta, as long as beta is in negative pi halves to pi halves. Right? Because cosine is an even function, and so when it's actually equal to the magnitude, but this equals cosine of beta if beta is in between negative pi halves and pi halves. Okay, so then we have, if we look back over at our equation here, we have VR over that value. So coming back up, VR, we'll just have a sine beta. So if we come back here, we'll say VR over cosine beta is just going to be equal to the sine of beta. And again, we do actually have VAs, and this is the point where they cancel out. Cosine beta, which is equal to the tangent of beta. So we then get this relationship where if we want to get beta out, we just divide V sub r by the square root of u sub r squared plus v sub r squared, take the inverse tangent, and we can get beta out of it. So now, by measuring, let's review this. We measure UR, VR, and WR, and we can then calculate first V sub A, and then we can calculate alpha and beta. Excellent. So this is all for this angle, or for the vector, our relative airspeed vector VA, a relative wind vector V sub A. So we can measure it, and then we can obtain those angles directly from that measurement. We can do a similar thing now for V sub G. So again, we're going to define two angles. So here's our V sub G, right? So V sub G is then used to define what are called the course and the flight path angle. Now recall that V sub G is the actual motion of our aircraft, and so the flight path angle, which we have depicted here, flight path angle, that's just measuring how far off of the inertial frame we are pitched up. Or not that we're pitched, because that would be our theta value, but that our vector is pointed up. So again, we're measuring off. This is measured off of the inertial plane, and we're just saying how far, what is the angle to get from the inertial frame XY coordinates, so the northeast coordinates. How do we pitch that up, or how do we pitch that frame up to get to our velocity vector? Okay. And our course angle is a very similar thing. We're just going to say, hey, if we project everything down onto a plane, and we look at the nose of our aircraft projected onto the northeast plane, what's the angle between that and the direction we're traveling, right? Sorry. We're not projecting the aircraft at this point. We're projecting V sub G. So if we projected V sub G onto the east-north plane, so the vector that the vehicle's actually traveling, and then we measure our course angle based on the angle from the north axis, I, to the direction we're traveling. Okay. So that's how we get our course and our flight path, define our course and our flight path angles. So now we can look at everything together. So if we look at a top-down view, right, we have right here we have our aircraft where it's pointed, and we point along what we defined in a previous lecture as psi. So the aircraft is pointing along, so if we're looking flat down, top-down view, the aircraft is pointed and it's looking along this vector. And that vector, this vector right here, that I'm drawing in red, is just an angle of psi off of the north axis. Okay, then if we look at our course angle, so let me erase those reds. So now this course angle, that defines the, again, projected down, that's the angle we'd have to rotate to get from the north to where we're actually moving. Right? So the course angle looks at from the north vector, how are we actually moving in the northeast plane. Excellent. Then if we look at our side slip angle, beta, side slip angle is defined based on IB, right, which we define using psi. So the side slip angle is defined again from psi plus the amount of angle we would need to get to VA. So here's that relationship. So that side slip takes us from our body x-axis to the VA if we're projected onto the northeast plane. Excellent. And then there's a couple other angles. We have our crab angle. So if we just look at that, the crab angle is actually very similar to the side slip, to beta. So it's similar to side slip where it's measured off of the body axis, the body I-axis projected onto the northeast plane, all the way over to, instead of VA, it gets measured over to a VG. And then we have one more vector, or one more angle right here. This is just going to be called basically the direction of our wind. And that's measured off of the north axis. And this is to the wind coming from our weather, right? So that's just the angle from the north to where our wind vector is pointed. Okay, and then when we look at the crab angle, I forgot to bring this up. It's just going to be our actual course angle minus our heading angle. So that gives us that difference. Excellent. Now if we look at it from the side, we can define the other variables we've been talking about. So here's our aircraft, and previously, again, this is projected. This is now projected onto a frame formed by IB and IK, right? So, or not IK, KB. So if we look at that plane, project everything down onto that plane, then we can define things really well. So we have our pitch angle, which will actually be coming out of the nose of the aircraft. We have our angle of attack right here, which is going from our relative wind vector up to that angle that comes out of the nose of our aircraft. Then we have our flight path angle. This flight path angle gamma just tells us from what is the angle to get up to our V sub g. So that's very similar to what we then will call gamma sub a, which is the angle to get us up to V sub a off of the plane defined by the northeast. The northeast vectors. Okay, and we have this relationship, right, where gamma sub a is just equal to our theta minus our alpha, which is a nice relationship. Okay, so these two views are really important. Make sure you understand these two views really well. Now, one last slide. When the wind speed and the side slip are 0, So when we talk about wind speed, in this case, we're saying that the magnitude of V sub W, so the weather wind, when that is 0, and our side slope's also 0, then we have some really nice simplifications that we'll utilize when we're developing trajectories for the aircraft. That our airspeed is going to be equal to the ground speed, that our velocity of the vehicle, so this is a velocity of vehicle, are just going to be the velocity. This is the same relationship as the velocity of A. So for some reason we switch that around because UVW just correspond to, these guys correspond to VGB. Okay. And our heading angle is just equal to our course angle, and our flight path angle is equal to the our flight path angle and this lambda A, or gamma A, sorry, are equivalent. And that's really simple because we can see that if VG is equal to VA, then of course gamma is going to be equal to gamma sub A. Okay, so there you have it. There's our wind triangle. And as we go through the book, we're going to reference this over and over and over again. So make sure you have really solid this relationship, what these 3 different vectors are, and then you'll know how you can get those vectors from various different components that we can measure.